but if you all you want to me to teach Mathematica, like the software that they use Mathematica for some assignment, integrate it curve, it's helpful. But then I can give you lecture.
So today you are our teacher?
No, I'm not teaching today.
But
But for the main course material, he will give lecture by himself. But only some, like I will be able just to help you, not teach you.
okay.
Should be open.
Nice.
Did you get my email?
Yes.
Okay.
I was talking before. I will be sharing the room with him.
With about 12 of us.
Okay. If you have to fill the form or
Well, chop chop.
send it to, I don't know.
Just go down there and do it.
Sorry.
Kaminar, walk. Walk down, fill it out. You have the form now?
No, I don't have it here. She gave me one. I have it at home. I will.
Okay, but she can sign for me
Okay. So
because she was copied on the email.
okay.
Paul, do you want to do the intermediate lectures on differential equations?
Which part? Differential equation?
Yeah, the review.
Okay.
You want to do that tomorrow night?
Okay. Do you have distance learning or just?
Of course. Yeah.
Oh,
No, not for me. Just you.
just
Is that too short of notice? Okay. Yeah. Well, you can do it some other time. But we should probably cover it. I'm going to do the first part of Laplace transform tonight, and I'm going to have to do some more. I found all my codes, but they're all in Excel 2003, and it really does not like 2010, so I'll have to fix all that.
I remember that Dr. Blanco used to give me the function in Mathematica about inverse Laplace. Do you want me to share that to them? No?
Let's keep it simple. Yeah, I know that one day we're going to do that, but not yet.
Okay.
I think I got all the videos straightened out too. Sorry about that. I was a little confused on which one was which. It happens.
And how to record the video?
In here?
Yeah, because when you are not here, I have to.
No, it's not on here. It's behind it.
Okay.
So whatever we do or say here is recorded.
Okay.
Everything from 7 o'clock until 9 o'clock, everything is recorded.
So we don't have to do it.
No, nothing. It's all. Yeah. If you log in, it records. If I log in, it records.
How about the voice?
Everything.
Everything?
Yeah. It's behind it. The system is behind the computer.
So we don't need microphone?
No, you don't have to do anything. It's totally, if you log in, it's my time, see? So it knows that it's me. So it sends the video to, it doesn't know who's logged in. It just knows that it's my time. So it takes a video of right now and it sends it over to the Echo system. What is this thing? Mickey Mouse?
Are you working tonight?
No, a toy. Did you like the toy?
University in New York.
Yeah? But do they allow this at Polytechnique?
Yes, I guess.
It's exactly the same as the iPad, huh?
Yeah, but it's more iPad mini.
Yeah. I've been thinking about it, but I was gonna wait until they had the Retina screen on the small one, but that's gonna be a while.
The difference, the academic system is not like technology. I guess we don't have it in mind, but we don't have it in the computer.
Here we go.
Know this stuff, and you can write on the screen, erase it on the computer. I can't imagine that. Maybe for the next few years.
The next generation.
Yeah. My generation is backwards.
And chalk. Okay, Chico. Jorge,
Yes.
you get to be last to get a desk. We have to wait a little longer.
Okay.
I forgot. So you get a good spot. It's Paul's old spot.
Sorry.
So whenever Matt finally finishes, we'll give him his spot. It'll be maybe 1 month.
Okay.
So it's a good spot.
Okay, perfect.
By the window, see the sun coming up.
Perfect.
Yeah. So what was good about today? Today is not $3 pasta day. You made me think that's important. You know? And what was good for you today? Big day?
I have 4 classes today.
4 classes. That's good. Well, you doing okay?
Yeah.
It was a good email this morning. I like somebody who sends a correction to their email and answers their own questions. That's my favorite. Do that. All of you do that. Oh, I just figured it out. You don't have to do anything. We call that self-medicating. You're all graduate students. So, what is this, a rabbit dog? So my neighbor here has a dog, and that dog has decided that I am his person. So he comes over to my house and waits for me, and acts like, you know, my friend. He doesn't get enough love at his house. And they got a new dog, so he's not the most important dog anymore. But I think he just likes me because I take him on walks, and he goes and runs and goes to the bathroom in other people's yards, you know? That's what dogs do. And we're out in the country, so it doesn't matter, you know, there's no, not like in France, you know? You just go. You're done.
But that's very new in France.
Sorry?
We just been doing that for 10 years.
Picking it up.
Yeah, before Christ was yesterday.
Yeah, in New York, where my wife went to medical school, when the springtime would come and the snow would melt, that's the word for it. It was a minefield. Okay. So tonight we have an introductory lecture to the Laplace transform, and sort of according to what I think is important, this is going to be the highlights. And next week I'll do a lecture on the special function, and it'll be the highlights. When we get to our problem solving, that's when you're going to really have to know these things. And as I mentioned before you came in, I used to have, in the past, I had a bunch of Excel files that would do the Laplace work that we're doing here, and I forgot when we switched to 2010, all of the capabilities disappeared. So, I mean, the function names are wrong and everything else, and now you have to go back. You know, Excel changed the way they reference functions, so we had to go back and fix that. So I'll come back to you later on. I don't know if it'll be 1 week or 1 month, but we'll get you some Stayfest algorithm files so you can play with that. Paul wanted to give you some guidance on how to use Stayfest algorithm in Mathematica, but let's do that at the end of the semester. And if they want to do that, that's fine. The only problem with Mathematica is then you become a slave to Mathematica. So, you know, that's your decision, your problem. Okay, so tonight we start by talking about what the Laplace transform looks like. It looks very simple. Maybe not to you, but to me it does. Gautier, do you remember why he defined it this way, historically? Me neither. And it can also be defined in this fashion. Now, why would you do this? Why would you define it in this way? Well, this is the definition of the Laguerre polynomial, or the Laguerre quadrature, pardon me, and so, or the Laguerre form. So we'll be using that. What's the easiest way to explain the Laplace transform? John, do you like seafood?
Yeah.
Like crab?
Yeah.
Yeah, you like crab? Okay. So, when I was a little boy in Louisiana, we would catch crabs. We would use a special kind of trap. We would put some food in here, and the trap had a special door, and the door would let the crab in. Of course, we got to put his eyes up here. And, you know, they got these little things here. Have you ever, anybody here ever played with crabs? No? If you grab them by these things, you paralyze them, you know? You never did that? Yeah? Have you ever been bitten by a crab? Yeah? Where?
The toe.
Yeah, everybody gets bit by a crab on the toe. And your eyeballs, they pop out of your head, right?
Right.
Because once he bites you, he's not going to let go. So he sees his food, and he says, I want to get in there. So that's the Laplace transform, okay? The food is that what happens with the Laplace transform is we reduce a partial differential equation to an ordinary differential equation, and I believe that Paul will demonstrate this probably next week in a special lecture. He'll cover the material on differential equations. It's actually in this section, but you use the Laplace transform to reduce a partial differential equation to an ordinary differential equation, or you can use the Laplace transform to reduce an ordinary differential equation into what? Into an algebraic expression. So you take something that's really unpleasant and you make it into something that's kind of easy or kind of nice. So again, he wants to get in there. Okay? So rather than redraw this, I will cheat and I will show you that he gets in. And over here is the food. So now he wants to get out. Uh-oh. This door, that's the getting in part. Okay? What's the getting out part? The getting out part, I don't want to hurt my crab yet. So how does he get out? This is the Moulin inversion integral. Do you remember this? Yes. Okay. This is a complex inversion integral. Here, here, here. The way it works is you have a pole in space and you have to go integrate around it. and then come back, that's what it does. Okay, I don't really care either. So, from a mathematical standpoint, what he basically has to do is he has to squeeze through the little hole here. That's what that does. That big crab is not going to squeeze through that little hole. That's the inverse Laplace transform. So getting in, the door lets him in easy enough. Okay? So how does he get out, GYD? Sure you do. What's rule number 0? Cheat. So how does he cheat? He's a smart crab. He brings a bomb with him. Okay? And that bomb is numerical inversion. You guys get it? So we're not going to solve the Laplace transform by coming out the door. We're going to solve the Laplace transform by blowing up the trap. So what happens to the crab? Sorry?
When it goes out.
Everything either works,
Where it goes
there's
through.
3 scenarios, right? Bomb blows a hole in the trap, and he goes out. Bomb doesn't blow a hole in the trap, he has to stay in. What's the next one?
Everything blows up.
Bomb blows up crab.
And that's an instance where you're basically saying that it's stable to go in, but it can be potentially
The Laplace transform is stable to go in, so you can get in the door.
But the inverse, when we're trying to get back out,
It's tough.
okay.
So we use approximate or numerical inversion to get out. There are cases where it doesn't work. There are a few cases. Usually, inverse Laplace transform algorithms do not like steps. Okay, they do not like things that go steppy. They also don't like things that jump up and down. But there's 3 scenarios. Everything works, everything doesn't work, or it just total destruction. Okay. How many different Laplace transform algorithms are there? It's fair to say there's probably at least 50 major algorithms, and then probably, grad student in math comes up with some variation or that sort of thing. But there's families of algorithms. There's going to be a family of algorithms that follows the cost or the, what was the name of that method? I'm losing my mind. Witter method. Witter showed, using the properties of the Laplace transform, that if you differentiate the Laplace transform, then eventually you end up with something that can be inverted. It's not particularly accurate, but it was a clever approach. It's going to blow up and take everything with it. It does not work well. Then what happened is Gaber came along, and his sampling method essentially amounted to the same thing that Witter did, but his sampling method was using finite differences, I guess you'd say, or finite pieces. Okay? So Witter and Gaber sort of had the same idea, that they were using differences or derivatives. Gaber, he really gets the Genius Award. Okay? You don't understand that because we haven't talked about this very much, but he's the one that figured this out. And then he essentially built an Airbus 380 and put toy propellers on it. You don't understand. He came up with this algorithm for numerical inversion. But the problem is, how many samples do you need? technically you need an infinite number of samples, but you can't take an infinite number of samples, and we'll talk about that in a minute. So how do you get to an infinite number of samples? You extrapolate. And he came up with a very simplistic extrapolation formula. I mean, to his credit, he solved the genius part of the problem, and then he said, this is the answer. It wasn't far enough. Stapes comes along and writes the shortest paper in ACM history. I think it's a page and a half or 2 pages long. And it's an extrapolation formula based on collocation polynomials for Gaber's algorithm. And that was the end of the story. So, you know, Gaber built this beautiful machine, only it wasn't plugged in. I guess that's the way you describe it. And then Stapes comes along and does something else. There's a lot more elegant discussion of this. And again, this is Dr. Valco's thing. But the way I like to look at it is read the Gaber paper. It's really a fascinating piece of work. And then read the Stapes paper. And your conclusion will be that Gaber did all the work and Stapes figured out the extrapolation formula. Is his extrapolation formula perfect? No. But what's nice about it is all of the estimates used in the Stapes algorithm are in the real domain. They're not in the complex plane. Then there's an enormous family of complex plane inversion algorithms. Why don't we use those? Well, because they're pain to program. Okay? And, you know, if you can come up with something where you can use an environment which, and again, it's Mathematica. Mathematica has the ability to push the precision to whatever you want, then, you know, the other methods aren't necessary. So, you know, you can have Mathematica run the Gaber-Stapes algorithm or run one of its children, and it'll generate really beautiful results. But it's not going to do it cheaply. It's going to take a long time. I've seen a case where Dr. Valco reproduced 100 decimals of sine using the Gaber-Stapes algorithm. You try doing that in Excel, you're going to get 3 or 4 decimals of accuracy. It's not designed for that. Okay, but, so there's the discussion. Laplace transform, inverse Laplace transform. And again, Paul will cover the discussion about how we apply it to differential equations. That's going to be a big part of what we do late in the course. Okay, somebody sent me an email last night, and they noticed that the due date for the final assignment is December 4th, and the due date on the syllabus is December 11th. I have a secret. That was a deliberate act on my part. I want us to target the 4th, but I'll leave the 11th as your absolutely final submission date. Okay. What do you call that in industry? You call it a stretch goal. You know, it's really 11th, but I'm going to make you think it's the 4th. Okay? Nobody's graduating. If you decide you want to go over into the next semester, that's fine with me. Because if you read what I wrote over and over again, all I want is your best work. Now, most people should be able to do this, well, everybody should be able to do this in the time that's given to them. But if you want to run over, I'm not going to stop you. But then, you know, if you give it to me in May, guess what happens to your grade? Because at Texas A&M, when one semester ends, what happens to the grade that was not issued that previous semester? It turns into an F. It's called a motivation mechanism. It's just a grade change. Nobody dies. It's all the same thing. And by the way, how do we do grade changes at Texas A&M? We do them on a piece of paper that was printed back in the 70s, and it has 3 copies. And it's all carbon paper, and that's the way it is. You don't get to change a grade by going like this. Change a grade, let's go to Eleanor, go to the department head, let's go to the dean, let's go to the registrar's office. They do hundreds of these a month. There's absolutely no problem with it, but just so you're in the loop here, it's done on paper. So I might change your grade, but it may take 2 or 3 weeks because they take them over to the dean's office, and what does the dean's office do? They make a big stack of them, and then the poor guy sits there and signs them all. Maybe someday soon they'll all be electric, or electronic, but not right now. Okay, and I know you're saying, well, that's not going to happen to me. I get it. It's not going to happen to you. Okay, so now let's talk about the Laplace transform. One of the nice properties of the Laplace transform is you can make a step function. The step function in the real domain, which you're looking at here, this is a step function. In the Laplace domain, it becomes 1 over s multiplied by a decaying exponential. This is really clever. This is really powerful stuff. Why? Do we have steps in the real world? Yeah. Everything's a step. Everything is discrete. We don't have continuous information. We have discrete information. When I was your age, nobody would have tried this. This wasn't really, people were not enthusiastic about looking at tables of information. You'll even see papers written about how to take the Laplace transform of a table of data. There it is. It's not hard, but you have to formulate it. So the first, and we may not cover this tonight, but the derivations are all given. The first one is a discrete step function, which is the son or daughter of this thing, if you want to call it that. The next one is the piecewise linear, and then the piecewise log linear. Why would you go from a step function to piecewise linear to piecewise log linear? Because maybe data is spaced logarithmically, or maybe data is spaced linearly and you want to capture the trapezoids rather than the steps. Rombaltis and Stewart proposed the first Laplace domain deconvolution approach using data. And so they needed to derive this formulation using steps, and then they, of course, they used piecewise linear pieces. Horn and his colleagues used step functions, and then Rombaltis and Stewart did this. And then I came along and I made it really hard, and don't worry about that. It's ugly, but it's not that bad. And so that's it. We can represent that in we can take a table of data and we can represent that table of data as steps. We can represent it as piecewise linear partitions, or we can represent it as piecewise log linear. Usually pressure transient data is spaced logarithmically. That's why I was doing mine, and that was why I came along. There's your answer. Any thoughts or questions about a data table? Everybody's okay with that? Let's see a show of hands. How many of you say, I'm never going to need a data table? Come on, Smock, put your hand up. Somebody give me nobody's giving me anything. I got it. Okay. That's the way you want to play. All right. So you think there may be some time in your life when you're going to take a table of data, production data, well test data, something, in Laplace domain, this is how you're going to have to do it. Horn had a student who performed a mathematical trick, and instead of doing analysis in the real domain, he expressed it graphically in the Laplace domain. It never caught on because it's not practical. Nobody cares. But it was a clever idea. You know, how are you going to get in the Laplace domain? You're going to have to use one of these approaches to represent your data there. And what this guy did is he had a cheat and, represented it in the Laplace domain. It's a clever idea, but it never caught on. We're interested in pressures and pressure derivatives and rates, and rate derivatives, and rate normalized pressure drop, and pressure drop normalized rate. We're interested in practical functions, and this is where something like this might come in. What about using a spline? Remember we talked about a spline, which is a curve that connects points very tightly. There's specific knots, and it goes through it. So maybe something in between using piecewise linear, use a piecewise polynomial. Is that necessary? How many of you have worked on field data? Yeah? Okay. Let's torture the Mexican and the Argentine for a minute. How accurate is your field data?
Not so accurate.
Okay, thank you. How accurate is your field data? It's perfect.
Production data, not accurate.
So is it within 1%, within 10%, within 50%? Usually oil is pretty accurate because we sell it, but I like that. But it's measured in tanks, and sometimes you might forget to count a tank. You know, it happens. Go ahead. Sorry.
And you measure a group of wells.
That's what I was really thinking about. Is you measure a group of wells and then you reverse allocate back to the one you're interested in.
And you have gas and water and everything.
That's the number one enemy, isn't it? Is allocation errors. Does every company have allocation errors? Yep. Everybody. What about deep water wells? $100 million well. Do they measure the rates on it? Nope, they can't. They can only measure rates on one or two at a time. So they rotate. This week, this well goes to the metering. Next week, that well goes to the metering. They develop a factor. They know the total stream, so that's why when you look at offshore rates, they're really clunky. They might be once a week. Sometimes they step it back to once a day, but that's usually garbage. Sometimes it's once a month.
Yes, once every 2 months. You have many wells.
I'm talking about $100 million wells, though. They don't even measure it more accurately than that, because it's gone. It went to the shoreline. You know. Now, in these $100 million wells, you have gauges at the bottom. Maybe 2, 3, 4 gauges sitting in the bottom of the well that are taking pressures continuously every second. So you have pressures measured every second and rates measured every month. These two are supposed to be the same frequency. How many seconds are there in a month? Well, let's just round up and say 100,000 seconds a day times 30 days. You know, we're off a bit, but you get the message. That's not a good thing. So you have 1 point in rate for every 2.5 million points in pressure. Oh, I didn't think of that. This isn't going to help you, but we need to think this through. So is that what you were worried about? How can you tell the data has been allocated?
How do they allocate?
How can you, no. How can you tell the data has been allocated? If you're going to allocate data, are you going to go to the trouble of putting in a decimal point? No. So if you see 1, 2, 3, 4, if you see all the data points in a horizontal line, it was allocated.
And also the people that allocate data many times, they see a change in the rate and they don't want trouble and they try not to explicit that change, so they do a small change. And then if that rate change continues, they in a period of time they get to the rate.
Okay. Are there other kinds of errors in rate? You guys remember, did we talk about orifice plates? You know what an orifice plate is? Yeah? No? Okay, so in a flow line, you put a plate with a hole in it, and that's how we designed our meters, is that the plate with a hole in it causes a pressure drop, and the rate is proportional to that. But that orifice plate, which is made out of super hard carbide steel so that it doesn't erode or anything, it has two sides. One side has a bevel in it, the other side is flat. There's a side that's sharp and the side that's not sharp. The sharp is supposed to go upstream. Every now and then when you look at the report and the rate changes, you'll read Bubba had the plate in backwards. I mean, this is like putting water in your gas tank. You know, you would think you'd pay attention to this, but people put the orifice plate in wrong all the time. How do you correct that? Forget it. You're done. It's over with. What happens if your measurements are out of calibration? I've seen $100,000 mass flow meters be out of calibration. You know, it happens. I've seen pressure gauges in a nearby friendly country that are operating on solar panels and they stop working for some reason. Do you know why they stop working?
Political.
The sun? Is that what you're saying? No, it's the birds. They like to eat, sleep, drink, and then have a nice place to use as a toilet. And solar panels, for some reason, are really popular. So I'm reading the report, and I'm like, this is a joke. But the platform's not manned, and so the birds just sit on the solar panels all day long and do their business. So there you go. Anything that's complicated, it can be broken easily.
So that way, I mean, with all that being said, the reason why you wouldn't, there's no reason to really get into the spline is because your data is not that type of
good.
big.
But you may have some, you know, if we step back and we're talking about analytic things, yeah, you'd want that kind of accuracy.
Right.
The other thing we didn't mention is that like in gas wells where you do have a meter online, they're measuring sometimes every 5 seconds. And so what you'll notice is there's this huge cloud of data points, and then they report one a day, that sort of thing. Is the rate really changing every 5 seconds? I don't know. I mean, there's liquid coming through this thing too, and when liquid hits the orifice meter, it causes a pressure drop, you know, so it's just bouncing all over the place. That's you're actually supposed to measure the gas after, you know, I don't know what's going on, but you'll see huge variations. You'll also see when pressure gauges aren't temperature compensated, they'll start wobbling like this. And, you know, I had a friend of mine who called me up and said, how do I compensate my gauge for, this is a small company, for temperature? I was like, what am I, you know, I don't know, I don't sell gauges. You said you work for Schlumberger for a summer, right? We're talking about downhole gauges, I'm talking about surface gauges. So how would you, if you were a poor, low-tech company, how would you fix your surface gauge so that it did not have temperature fluctuations? This is the real world. He went to Walmart and got a styrofoam ice chest, put it over the thing, wrapped it with so much duct tape it'll take a year to unwrap it, and no more temperature problems. That was his insulation approach. Okay, Paul, this is what I want you to cover in a separate lecture. This is our discussion. The Laplace transform of a derivative is the product of the function multiplied by one of the S parameters. It's a little bit hard to explain in a simplistic sense, but let's say we were just looking at the second derivative here, and what would happen if we're looking at the second derivative, this would be S to the n, which is 2, f of s, this would be 1, that would be the function at time equals 0, and then this would be s to the 0, which is 1, and this would be the derivative at time equals 0. So, you know, something like that works out very well. You guys got this? Now, in our case, we don't deal with second derivative, we deal with the first derivative. So what happens whenever we're looking at the first derivative, so this is just 1 and 1, so we get that, and then this, of course, is 0. So we need to know the function value at time equals 0, and then we have s, f of s. If you were really clever, what would you want the function value at t equals 0 to be? What's the best value?
0?
Yes. Why? That means we don't have to carry it around. So we're actually going to use the initial condition on our problem to force the function at time equals 0 to be 0. So our initial condition is always going to be, well, I mean, as often as we can make it 0, we're going to make it 0. There's only like 1 or 2 papers in all of the petroleum engineering where it's non-uniform and it's not equally 0. But when we get to defining this at the end of the term, you know, when we look at these differential equations, we are going to set our dimensionless variables up to where it's at. So would you use dimensionless pressure as pressure, or would you use dimensionless pressure as pressure drop? I just gave you the answer, of course. It'd be pressure drop, because the pressure drop at time equals 0 is 0. 0 multiplied by anything, which would be the characteristic pressure drop, is 0. So we're going to use this piece of information to define our initial condition. So you really want, you know, thinking about it a couple of months from now, this would be your best option. Would be to do something like that. To define your problem so that you end up with that being 0. Okay. And then, as I said, Paul will explain this, but the derivatives then become the coefficients of the differential equation. He'll show you how to work that out. These are all book problems. The ones in these notes, they're all ordinary differential equations. They all have nice algebra. They all work out. Now, you know, I say that, but there's a couple of really ugly ones in there. I think it's Sean's outline problem 242 or something like that, or whatever the case number is. It is really an ugly problem. The reason it's ugly is because the algebra doesn't really decompose and you have to use partial fractions, but they're all book problems. They're not things you're going to see in the real world. Okay? They're just exercise. And feel free, Paul, however you want to do this, to go ahead. Why do this? We're never going to have problems like the book problem. We're going to have real problems, which are actually partial differential equations, not ordinary differential equations, et cetera, et cetera. But going through this exercise is really cool. And Paul will explain this if he wants to. What's the easiest way to solve a differential equation? That's one. Separate and integrate, sort of the same thing. Anything else? Okay, that's everybody's saying separation of variables. Let's come up with another method.
Change variable,
Sorry?
like you change variable and find a new variable, depending.
Okay, hold that. You're going in the right direction, but you're not saying what I want you to say. But you're definitely, you know, you're walking around in the minefield and you're standing on top of France's nuclear arsenal. Okay, so just give me a second. Don't come back to that yet. Anything else? What about method of undetermined coefficients? Do you remember that? The differential equation solution method. Method of variation of parameters. Know how to English? Okay. What about numerical methods? Picard's method, Euler's method, etc. There's a, you know, read the Shams book. They walk you through all of these. But what's the easiest method? Okay, he said transform. If it's a book problem and it actually has an answer, this is the best approach. But of course, in the real world, we don't have these simplistic formulations. Okay? Everybody take a deep breath. Our problems are different than these. They're not harder, they're different. Okay, so what's the easiest way to solve a differential equation? The easiest way is by inspection. You look at it and you go, that's Legendre's equation, that's Bessel's equation, that's Rodriguez's equation, that's a Hermes equation, whatever. You guys got that? So this is why we have to practice, this is why we have to train, this is why we have to think. So in this class, we're not really going to solve the differential equation when we get to that part of the course the hard way. We're going to solve it by inspection. But the reason it works is because we spend all this time preparing the problem. And it so happens that cylindrical coordinate system yields Bessel's equation. It so happens that linear coordinate system yields an infinite series type solution, some sort of, it's not exactly Fourier series, but something like that. Okay? Okay. Everybody's happy? Everybody got a nice deep breath? Why didn't you become an insurance agent? Wouldn't that have been best to become an insurance agent? No? That's the least not an agent, but sorry, somebody who studies how people die and that sort of thing. That's an actuary. That's the least stressful job in the world. Except maybe for being a faculty. But, you know, it's supposedly the least stressful job in the world. So why didn't you do that? So what's the least stressful job in engineering? Besides being a civil engineer. Santiago, what were you educated as?
Natural engineering.
Natural engineering?
Industrial engineering.
Industrial engineering. At where?
University in Monterrey.
Okay, UTB or?
No, Catholic University.
Ah, the good one. Okay, yeah. Stick your chest out. Okay. Smapak, what was your basic degree?
Petroleum.
Yeah. Why didn't you go into something else? No idea? I don't have to ask you. You guys? First degree. Okay, so it's kind of, I got it. First degree. Same thing. First degree. Okay.
General engineering.
General engineering. Is that like general engineering? Okay. So, what attracted you to petroleum side?
Sorry.
Sorry?
It's a long story, but many things.
We have time. Oh, you don't, I forgot, you don't want to tell your story on the camera.
I don't know, I can't.
Yeah. Okay, well, we don't have that much time. So, how many of you remember your electrical engineering class?
Electrical.
Electrical. Do you enjoy that?
I ended like it. Yeah.
Okay. You didn't like it. You didn't like it. You didn't like it. You don't count. Did you like it?
High school, I liked
Why didn't you like electrical, or why you did like it? Okay. Well, you got this different personality. So you don't. We'll deal with you later. So why did you like electrical engineering?
Because it was difficult, one of the most difficult courses, career. I ended understanding many things.
Good answer. Now, in electrical engineering, does the problem define them, or do they define the problem? When you design a circuit, you design it to do something specific. Electrical engineers use Laplace transforms, but their problems always work because they design the circuit. So they have a relatively small book of Laplace transforms. Okay. But petroleum engineers, we don't design our problem designs us. So we have to do something, we have to accommodate the problem, not the other way around. And I'm not making fun of electrical engineers or physicists or anybody like that, but in their case, they have the luxury of designing their problem to give us a particular output. Remember, their role, primarily in electrical engineering, is design. I know there's a lot of signal processing, blah, 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 but when they're designing something, it has a specific output. This course, for them, they would love it. Because you show how to set the problem up, you show how to solve it using Laplace transforms. Bang, bang, bang. They're going to do that all day long. We don't have that luxury. Okay, now we're starting the part where you're going to either love it, hate it, or have to go on drugs. Okay? This is a discussion about how to take the Laplace transform using numerical means. We are not going to use this very much. You can pretend you're paying attention, because this is not where we're going to spend all our effort. But we have a situation where we want to take the Laplace transform of a continuous function, of a data table, of whatever. In this case, the Laplace transform has a specific form that is defined by the Laguerre quadrature formula. It is a coincidence, okay? So, why is there an approximation here and not an equal? Correct. It all depends on how many terms you take. So if I make n go to infinity, this becomes a definition. Is n equals 64 enough? For some problems it may be, for some it might not. Is n equals 16 enough? For some problems may be, for some problems not, and so on. So we'll talk a lot about this because there are some inserts in, well, we won't talk a lot about it, sorry, I shouldn't have said it that way, but we will at least look at, you can use this to reverse solve for what? For the inverse Laplace transform. So if you know f of s, you can reverse this and solve for f of t. This is f of t, by the way, and you're evaluating it at this argument, and that's not easy, but we'll talk about that a little bit later on. We may or may not give you a problem with this. What you're going to end up with is having to define this in some sort of a polynomial form. Are polynomials particularly representative of functions? Based on what we've talked about the last two times, would you expect a polynomial to represent a general function? Yes, no, maybe, not exactly. What's the answer?
It generally can, as long as you expand it out together.
Okay. So the likelihood of this approach working is probably going to be limited to polynomial and friends. And then it will give you an exact answer. Okay. There are probably ways of improving this on a sampling basis, but for the sake of argument, this is what we're looking at. Okay. If the function is polynomial, because Laguerre quadrature is defined on a polynomial basis, it'll probably work out very, very well. There's a relatively simple test. Okay. Just try it. Try the logarithm. Okay. This is the Gaber and the Gaber safe-S algorithm. Before you hit yourself in the head with a hammer, this is not as bad as it looks. Okay? So the Gaber algorithm is a sampling formula. That's why you see the log of 2. And then there's all these factorials and binomial forms and everything else that pop up. But this is the Laplace transform. This is time. This is the natural log of 2. And this is an index counter. So we can estimate this function given anything. This is the sampling part. The sampling. Okay, this is the engine of the Gaber algorithm. It also goes from n equals 1, or whatever you may want, to n equals infinity. This is in what happens as you start moving up with different values of n. Smug? N equals 2, not very accurate but stable. N equals 4, not very accurate but stable. N equals 6, getting more accurate, still stable. N equals 8, getting even more accurate, still stable. N equals 10, and so on. N equals 14 or 16, on most computers, this starts to break down. Why? Somebody tell me why.
You're pushing right before the Laplace transform. You have a factorial, and it's getting larger and larger and larger, isn't it? And so it's pushing towards 0.
That's the problem. The alternating sign. You're absolutely right that where the truncation or where the round off is occurring is as the factorials get larger and larger, you're adding and subtracting numbers in the series. And sooner or later you're going to hit something that's going to explode. But it's because it's an alternating sign series. You want an A in this course and never have to come back? Figure out how to convert this to a positive sign series. You're thinking about it, aren't you? Okay. Now, the way the Gaber Stayfest algorithm works is Stayfest uses exactly the same engine, but it uses a different sampling, like I said. So all you really have to know is these beats of i's. These are just numbers. This can be calculated. Don't be afraid of them. These are just numbers. You can make a table of the coefficients and just propagate it out. They're just numbers. I'm about to do something stupid, so stop me. Don't ask me. Why does, whenever you change a file name in Windows 7, it takes a long time before it allows you to rename it? Like if you copy something, maybe it's the way our system works, because there's a local backup as well as a server backup, or the main file's on the server, but there's a local backup. But what I find is you have to come back like hours later if you want to change the file name, and yeah, you don't care. It's like talking to children about income tax. All right. Here's the coefficients. They're just numbers. Okay? So for 2, you get these 2. For 4, you get these 4. For 6, you get those 6. And then after that, they're non-integers. They start breaking apart. Okay? After 6. That's another issue probably, but that's okay. So up until then, they're integers, and then they just go across the page. But you could store these values and use them however you wish, but those are the numbers for the Stayfest algorithm. Okay? No problem? They're just numbers. And what they're used for is in the extrapolation formula, which is here. Sorry, I'm pointing with my finger. This is the coefficient, and then this is the extrapolation formula that Stayfest provides. Okay? So, the numbers get bigger and bigger and bigger. And what were you saying happens, Avery? The bigger they get,
Well,
and they're alternating signs, something's gonna break sooner or later.
after I said that, I was trying to rethink. So K is pushing towards N, so you have N minus K, and the difference is getting smaller.
Yeah, but look at the values out here. You're 10 to the 9th, 10 to the 10, you just keep going, and it's just gonna keep getting bigger and bigger. Sooner or later, I mean, look at those digits. Sooner or later, this thing's gonna break. There's no way. And I'm not an expert on series convergence, but this thing is not gonna work. Okay. So that's the Gabor-Stapes algorithm. Everybody happy? Sad? Don't really care? It's just numbers. So, in theory, you could just store those values, or in practice, and you could use the Gabor-Stapes formula and simply put your function in and add it up and go. And like I mentioned, at about 12 to 14, this thing really goes haywire. Now, you can go into mathematics, or you can go into quadruple precision and maybe extend it out to something like 24 or 26, but even then it's iffy. Why is it even? Why do you have to have even number of coefficients? I don't know. It's the way Stapes derives it. It's got something to do with his polynomials that he used. Okay. So this is actually really straightforward, really easy to use, and that's why we use it. It's just not particularly accurate. And if you want more accuracy, what do you have to do, Paul? You have to go to Mathematica, and you have to use an alternate version of this algorithm that Dr. Balco uses, right? And what does all this equate to? Time. Okay. Okay, that's the end of that section. And this is discussion on the piecewise data functions. I probably don't need to cover this in a lot of detail. I just want you to be familiar with it. And what you do is you essentially integrate each step, and you do so over an interval, and then the last step, of course, is extrapolated to infinity, and that becomes the Laplace transform step. So when you integrate each step as a Laplace transform, you're going to get a multiplier with the exponential term, and that's what all this looks like. So this is really not all that hard. This is actually quite easy, because over an individual step, the step is constant, so you can see that the terms factor out as constants, and you just integrated the exponential term. So there's a sampling here for this particular term, and then you just keep adding them up. And when you're finally done, you have an expression when we're finally done, we end up with this expression that is relatively easy. So we simply use the individual values, and you can see this table shows that, and you write this expression for it. So it's relatively easy to just write this expression, and that's what I've done here. There's your expression for that data table. And that's probably more than enough accuracy for what we do. You can probably get away with just using rectangles. Questions, comments? No? Yes? Go ahead.
I just look at it. I mean, I'll look at this later, but so the S is just
S is a Laplace transform parameter. It's think of it as a scaling multiplier. So you have e to the minus st, so when you do the integration, you have to carry the st, e to the minus st along, and that's where it comes from.
Okay, so it's the, okay.
Yeah, and I mean, you have limits, so you're evaluating it over individual limits, and that's where the t goes away. So, questions, comments, thoughts?
So what do you say the Laplace transform comes at the last term of the...
Oh, because the last term is when you integrate it out at t to the n. I think maybe it didn't matter for this one. Maybe we automatically treat t to the n as infinity, or t of n at equal to infinity, and that term goes away. I'm not looking at the whole thing right now, but you have t to the n equals to infinity here, so that term just goes away.
Is negative infinity is 0. Right?
Zero. So it kills the last term.
Right.
And again, I don't want you to focus on this too much because it's really more about exercise. It's about understanding why we did this, what it means, and so forth. Yes?
And maybe my question is a bit light, but is there any bisection between the function and its Laplace transform?
Any?
Bisection? Right. So that might you have one solution, and when you want to go back, one only solution. I mean, if you want to embrace the Laplace transform.
You mean, are there tables?
No. Is there only one solution?
Oh, yes. Yes, thank you. There is only a unique inversion or a unique Laplace transform. Thank you. That's what you're saying by solution. Okay. Yeah, no, there's only... I'm sure you can come up with a problem that wouldn't be true, but from what I can tell, there's only going to be one solution. Wow, what a great question. Okay, this is the piecewise linear part. This is Rombalsis and Stewart, and basically, you just have to connect the dots, and then you have to write an equation for each of those connections, and you're integrating that in a piecewise fashion. I won't kill you with it. All the detail is here, but when you end up at the end, what it looks like is this. So you have a 1 over s squared term because you're working in time. That usually is a product of that. Then you have the slope term. You can see these. So this is the first term, and then the last term got knocked out, but the next to last term is here, so these two kind of look the same. There's a 1 minus e there. But then in the middle, all of the other terms are related to each other in the interior. So on the endpoints, you're going to have separate terms, but in the middle, they'll be combined. So, again, it's all just algebra. And if you look carefully, the multiplier on each one of these is 1 over s squared. We'll talk about that later, but that's a time variable. So these were all time functions. It was y is equal to mt plus b, and that's what happened here. So all of these t terms became 1 over s squared. And again, this is just exercise. The next one, I don't want to give you a real headache, but it's the same process, that instead of using piecewise linear, you're now using piecewise power law functions. And so instead of using y is equal to mx plus b, you're using y is equal to ax to the b. And so what happens is you end up with incomplete gamma functions, and when you work out all the algebra on that, you get something that looks like this. How ugly is equation 21? It's ugly. But let me tell you a secret. This is the only term that's really important. So you can eliminate all the other terms. I mean, they're important, but that one dominates. And this is one of those cases where when I was doing my dissertation, I went to the math department and I was explaining to them what I'd done, and I truncated the series and just used a single term expansion because the regular gamma function has some nice characteristics. And they said, oh, you stupid engineers, you know, this is wrong. And I said, well, when I do it that way, I get less than 1% error. And they literally said, get out of my office, you know, and that's how mathematicians view engineers. But I knew that I wanted to have this term dominate, and it just, whatever the forces in the universe, whatever you want to call it, it worked out in my favor for that. So that was 30 seconds of your time to explain something I did a long time ago. Okay. And then the last part is a discussion about the numerical Laplace transform. And in this case, what we're going to do is we can use the Laguerre quadrature formula, and we can represent, this is the definition of the Laplace transform, this is the definition of the Laguerre quadrature. We need to get this into a form where we can use that, and so, you know, when you make the substitution, this is what you get. So if you want to use Laguerre polynomials or Laguerre quadrature to represent this system, there's your answer. Now, again, there's probably very little practical use of this. I just wanted to show you that there is an elegant way of taking the Laplace transform of a continuous function numerically, and this would be it. So if you know f of t uniquely, then you can estimate f of s in any way. And again, it's really thinking about analytic functions. There are problems in nature that look like this, where you have f of t and t. You know, for something that looks like this, no big deal. But you will have problems that will look like this, and that's going to be a big deal. That's where something like this might help. Okay. Just as guidance, that's where something like that might help. Because that f of t is going to be really ugly to try to represent the Laplace transform of that. Okay. Now, having said all that and told you that we're not going to use it, let's go to something we're never going to use, ever, in a gazillion years, and that's the so-called Witter method. The Witter method says that what you need to do is take the nth derivative of the Laplace transform. The nth derivative of the Laplace transform. How big does n need to be, GYD? You can imagine the first derivative, the second derivative, the third. What about the 20th derivative? What about the 30th derivative? This becomes really impractical really fast. When you take a look at our functions at the end of the course, you are not going to like the first derivative, much less any of the others. Okay. So what Gaber did is instead he set it up as a difference, and you can see it's designated like this. Okay. So instead of being a derivative, it's set up as a difference. This Gaber's formula is very similar in concept to Witter's formula. I sat down one day and I tried everything I knew how to do to get that -1 out of there. But it ain't going to happen. I thought about remapping it, doing something different, but it's not going to happen. And that's where your problem lies, in applying the Gaber formula. So both of these are sampling functions. The Witter method is sampled as s is equal to n over t. The Gaber method is sampled at natural log of 2 over t. Okay. So All you have to do is take the difference and then evaluate it at the sample point, and there's your answer. Easy, right? Wrong. Like I said, you can try the Witter method if you want. And the papers are in the lecture. They're all scanned in and ready for you to review. The Witter method does work for some simple problems, and that was, I think, what he was trying to demonstrate. The Gaver method, of course, works for other problems. So let's look at a quick application of the Gaver method. Okay, again, here's the Gaver Stafest algorithm, or Gaver algorithm, and the Stafest algorithm. So if you were going to test the Gaver algorithm, we're going to evaluate f of t is equal to exp of minus p. So f of t is equal to e to the minus p. Okay? And we're going to evaluate it at t equals 1. So f of t equals 1, not 0, damn it. That's exp of minus 1, and that's equal to 0.367879, okay? And what Gaver did is he estimated this using his equation at n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, 7, 8, 9, 10. Is this clever or what? This is exactly what you would do, right? You would evaluate the equation at different n values. Okay? Everything's going along fine, and then what happens? What we need is we need this. We need the extrapolation, and we need to be able to estimate that point. Fine. But you'll notice that out here at 18 it does that, and at 20 it does that, and at 22 it does that, or whatever the number is. Okay, it's just good haywire. Okay. You can even see here at 17 we went off trend. So Gaver invented this very elegant, nice thing. Only it doesn't work. It has to have an extrapolation formula. Does everybody understand that? You evaluate Gaver's algorithm at these points, and then somehow you make an extrapolation. Okay? Well, the answer is Stafest came along a year after this and figured it out, or 2 years after this, and figured out how to use Gaver's formula with an extrapolation term, and the Gaver-Stafest algorithm was born. But what Gaver suggested was, instead of using n, let's use 1 over n. So here it's plotted as 1 over n. So there's your bad point there, and then you have this. Well, it's not bad, it's just 1. So that's n equals 1. And this is n equals 20, and you can see, well, it's not 20, it's 17, sorry. So, this is n equals 17, this is n equals 18, and then n equals 19 is down here. You don't see it, but it goes like that, and n equals 20 is up here, all right? Well, it's over there, whatever. So, what Gaver said you should do is you should use a 1 over n polynomial. So we'll take this and we'll write an equation, and it'll be f of t is approximately equal to what? These values, all right? So you've got f of t hat, if you want to call it that, is equal to f of t plus A1 over n plus A2 over n squared plus A3 over n cubed, and so on. This is your correct estimate. Okay, that's at, sorry. So this would be your value at n approaching infinity. Okay. So how did it work out? Well, the right answer is here, and the 5-term approximation is here. So we got 3, 6, 7, 9, oops, that's an 8, that's a 9. So it starts failing in the 4th decimal place. So that's what happened with his extrapolation formula. And by the way, if Gaber's algorithm fails, is Gaber's safe test going to fail? Yes, no, or maybe? Think about it. If the values, the Stapes algorithm uses the values from Gaber's algorithm, right? So if Gaber's algorithm generates the wrong number, what's going to happen to Stapes? You guys understand? So when we get to 16, 17 terms with Stapes, what's going to happen? It's going to blow up. So the Gaber algorithm is the engine behind the Stapes algorithm. That's the nut and the bolts of it. Okay. You guys got that, or?
And so,
Sorry?
and so that, no, I didn't split my thoughts, sorry. So even though that the Gaber had the extrapolation, it can only extrapolate for a few more terms before.
Well, you have errors. So you're going to have something, either A, you're going to have something that's smart that figures out that those values are wrong, or you're going to have to limit yourself below those values. And that's what I was talking about with the crab trap. You don't know where that is.
Right.
It might be 12 on one problem, it might be 18 on another problem, it might be 8 on another problem. That's why you're always going to see the Stapes value be a variable. And you'll have to play with it. You'll have to test it.
Trying to see what that upper limit is before it breaks.
Yeah, it's very straightforward. You just keep testing it until it breaks.
Sorry. A in the second part is the number you showed before.
Sorry?
The A1.
No, these are just junk. This is the answer.
Okay.
That's the value that you want. That's here. So you have to have these terms and then make the extrapolation.
Okay.
Okay. And that's exactly what Stapes did. He just doesn't report those other terms. He just reports the answer. That's the easiest way to explain it. There's a collocation polynomial in there, but he only reports the terms used. So I used to give this as a challenge problem. You come up with a better extrapolation model. Okay? How would you do that, John? Let's test some ideas. You guys think I'm an idiot, but I know what I'm doing. All right, so we have a plot of information, and let's say it's f of t, and here, well, it can be, let's say it's f of n in t, and here's the function evaluated as n equals 1, n equals 2, n equals 3, n equals 4, 5, 6, keep going. T is constant, okay? The exact answer, so this is f of t exact. Whatever that value is. So what are these points going to look like? Well, let's start here, 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 here. Maybe I'm not drawing this aggressively enough, but I wanted you to understand what it might look like. And then we go out to 13, and the point starts to drop, and we go out to 14, and the point jumps up. Okay? So I still need this value. How do I get it? I need to know to be able to get to that extrapolated value. How do I do it? Whoa. It's psychedelic, man. I've been staring at that yellow. You guys are all green. So how do I do it? Santiago? You don't get a degree unless you tell me how to do this.
No.
Right now. Right now. Were you in the Army? No? Shooting at British people? No?
No, it's very young.
Not yet. Do you remember the guy that we had in the class? The guy who had been the captain of the boat? The old guy with Petrobras? Yeah. Yeah, he'd been trained by the Americans. Remember what he said? I don't want to fight nobody. So how do we do this? I need you to tell me how to get the green line.
Make a function.
Yeah. Tell me something. What did what did Gaver use? Gaver used f of n t is equal to f of n equals infinity t plus a1 over n plus a2 over n squared plus a3 over n cubed plus ... He used an inverse relationship. Obviously, this is the answer. This is the value we want. This is the energy. Somebody give me another equation. Juan? Mr. Song? No? KJ? Look in the back of your head, not in your book. Does anybody have an idea? So what did Staples use? Staples used a collocation polynomial. What does the collocation polynomial do? It goes through every point. So once the error starts coming in, what happens to his collocation polynomial? It's going to pick that error up and it's going to be wrong. But his equation, it's not going to look like this. It's going to have a different appearance. But it will have a term that's related to what would happen at n is equal to infinity. Anybody have any idea?
I mean, you poorly serve just to take the last set of points, or the last several set of points, and just continue linearizing it.
Okay, but what you're basically telling me is that you got to have some smartness that after this point, you know, what is it, skull and crossbones?
You're in some trouble.
out there, right?
Right. Because unless we have something else, I mean, it looks like it's wanting to push as close as it can. The problem is you don't know if the exact rate it's trying to go. I
Well,
don't have a-
this is all still 1970s type discussion.
Right.
We haven't talked about anything fancy, anything. I just want to see if anybody in here has any ideas.
I mean, the only thing I would look at, I don't know, is look at how the rates are changing, how the slopes are changing.
Okay, so you're suggesting that we come up with some sort of a differencing formulation.
In essence, and see how it's starting to slow down, and then you could try and extrapolate that rate at which it's declining the slope of the derivative.
So you're saying, if I understand you, that what you really want to do is you want to plot the derivative.
So we've got the derivative, and then we'll have the second derivative for the rate of the
Stop saying second derivative, let's get through this one first.
Sorry.
It's going to drive me nuts. Okay, what's it going to look like, class?
Like 1 over.
It's going to come down like this. And gradually, I guess this will be 0. I mean, I assume it's going to be well behaved. But what I think you're trying to say, and of course, it's going to blow up out here, but I think what you're trying to say is you're going to watch this, you're going to extrapolate this instead.
I guess that isn't quite.
That's pretty clever.
And then integrate it.
Hmm?
Once you-
No, I don't know. I don't know what he's going to do. What he's looking for is how to extrapolate this behavior.
It is the same problem as the first one.
Sorry?
It's the same problem as the.
I think so too.
But
I don't-
it's just like decreasing.
I don't think it's going to, it might help you if you formulate it as some sort of a combined, maybe like a Taylor series or something? Is that what you were thinking?
No, I mean, I guess I had it flipped. What I was trying to think is, if you go between the points, so as you go from 1 to 2, and you just do kind of a straight, like a linear, you try and start linearizing it, and you're getting a slope, and then as you're connecting your points, the slope starts flattening out, which is that. So then you just kind of continue, you have to see what that rate is and then just continue it. But I guess,
But its destination is 0.
right. So in essence, it's continuing that and just taking the mirror of it.
So what you were thinking perhaps is to use some sort of a function here, and then you would know its integral, and that would give you the value, I guess?
Yes, and that's the same problem.
Anybody got any other ideas?
Get better data.
We need a function that has a limit. Then again, exactly the same with the Taylor series and the polynômes. We can extrapolate on a series of functions that have some limits and find
What he's
coefficients.
saying.
And as we have like 9 values in 9 coefficients to put the right function, and each of them has to have a limit, an infinite limit, like finite infinite.
So, you guys remember Jerry Reed? You wouldn't know Jerry Reed. Sang a song back in the late 60s, early 70s. What was the name of the song? When you're hot, you're hot. And when you're not, you're not. I think this one, probably thousands of people have busted their pick on this, trying to figure out a solution. But one of you is going to break it. When you study the work they did in the 50s, when they were using Laguerre polynomials, it was so elegant and so for lack of a better word, sexy. It looked like that was the answer, but it blew up immediately. It was just junk on any kind of problem that was non-polynomial. Polynomial, near polynomial, worked perfectly. Non-polynomial, forget it. So I think that's where we're going with this. It has to be general. Now the clever thing about looking at it as 1 over n is you squish all the values that you're projecting them. Has anybody got a suggestion other than 1 over n?
Would you do it even more? I mean, by
Hey,
trying.
just because I'm up here doesn't mean I know the answer. Okay, so this will hold you till next lecture. Somebody's going to wake up in a sweat and have an answer for this. It's going to be you?
No, maybe an idea.
Well, speak your mind.
An exponential minus t.
So you're thinking it decays like that?
Yep.
So what you do is you plot this as a logarithm and see if it...
There is a function with an exponential minus t.
But this is e to the minus t, then that's going to be what? If this is whatever z is equal to a exp to the minus b times t, what's this going to be? It's going to be 1 minus a exp, actually, sorry, it'll be, if this is z prime, then z will be equal to a times 1 minus exp minus b times b. Right? You may be on to something here. Sorry, not t, not t, not t.
And
Thank you.
if you sum those terms,
No, but you suggested an alternate form. Correct? Now we're no longer polynomial. What is A? A is the right answer, isn't it? As we go n equals infinity, what happens?
yes, I got it.
So A is the right answer.
I would do it for short, to get a one times A.
This might work.
And then what would the negative b term be?
Just junk.
Just some other.
Something to carry on.
Okay.
I mean, what he's proposing is just this looks, smells, and tastes like a exponential decay. By looking at, you suggested it. You said it's going to go to 0.
Right.
And he just extrapolated that into what this might look like. Paul? Is it going to work? Santiago hates this. 3 options. Okay. Why will it not work?
Are we still at a basis where we're using the same data that once it gets to a certain point?
Yeah, of course, but you'll still have to stop it. But do all problems look like this? That's why they use the collocation. Because we've assumed that it behaves like this. May not. But this could be a clever formula. Especially if we start mapping this, because we can do that. We can map the derivative of this and see what it looks like. That's a really good idea. Well, you guys. You can call it the GYD AD. So what's that? GDAD. So Interesting. What you're basically getting out of me is you have to go on ahead and pay for these estimates. No matter what else you do, you have to evaluate the thing up until the point where it fails, using the Gaber algorithm. You have a finite number of samples. Does everyone understand that?
Yes.
Regardless of this, you're going to have to specify N max is 12, or N max is 16, or N max, and you're going to do that by testing. Yes?
So then in application to an extent, we have the ability when given the data to extrapolate to a point in time, but then past that really...
It wouldn't be time, it would be N, but yes.
Sorry. But then at a certain point we kind of have to have that break before we get a new set of data that pushes us further along. So we kind of only have a distance past that we really can...
Well, and the other thing is in actuality, the value N max will vary over time.
Okay.
For a given problem,
Mm-hmm.
N max may vary from 6 to 18 or whatever. I'm not saying it will. I mean, in general, the more terms it should approach a higher accuracy. But we had this problem back in the 80s when we were doing all this programming and we're trying to figure out the best N value. And we realized that for certain time range, N equals 8 was better than another time range. So this is actually time dependent, or N dependent. That didn't come out right. It is dependent on N. Sorry. Okay, so our next discussion on this will be actually, I'll give you some code. It may be a while. It may be before I make the assignment, but we'll give you some code on the safest algorithm. And you can bet after this discussion that part of the problem will be you take the Gaber algorithm and come up with your own formula. And I don't mind, let's say, that I'm kind of looking at diagonals here, talk about it, but you got to do your own thing. And if everybody comes up with the same answer and it's this, I'm going to be disappointed. Okay. So what are you going to do? Gautier?
Like nap.
You going to take a nap?
Yeah, it's a picture.
Sorry? Oh, you're going to? It's coming on the feed. Okay. It's America, man. We copy everything. Sorry, we make a recording of everything. Don't you remember the Nixon White House? All right. I'm pleased. We had great engagement tonight. Probably because Ralph wasn't here. What does he like to be called?
God.
No. What does he really like to be called?
Calling you Gab.
Gab? It's kind of a girl's name here.
You can't let people Daniel. You would have called him Dan. So
No. Gabrielle is usually Gabby.
okay, yeah.
Yeah, we'll call him Gabby. That'll make him insane.
Gabby
Gabby?
shoot.
What's...
When you like shoot, it's like Magneto.
Oh. You're a good boy.
That's been recorded,
Yeah. Last chance. All right. Okay, so our next physical meeting with me will be the 3rd and 4th of October. This has nothing to do with you. It has to do with me. Sorry. I agreed to a bunch of travel before I realized it was all on top of each other. But we will work next week at 7 o'clock on Tuesday and Thursday. Okay. I hope the internet is strong enough. We may have a couple of false starts, but we'll do the best we can. Paul, I don't see a phone number here. I don't know what the number is to this thing, but find out what it is. So if I have to call you on my satellite line, it's stable enough to use for the phone, but it's not stable enough to transmit over, I don't think. We'll see what happens.
And maybe this is me being archaic, but so when you're gone, does that video screen activate so it's almost...
No, he will be up here, he'll log in under his address, we'll connect using a product that the university has selected. It is not my favorite product because you have to go through multiple steps. Basically, we have a trial version of it, and you have to set up a meeting, send yourself an email with a web link, but he and I have it all worked out. Our backup is Skype. The quality on Skype is probably going to be a little sketchy, but we'll get there. At worst, I will give him the slides, he will project, I'll be watching, and I'll say, okay, this is this and that's that. But probably we'll do what we're doing here.
Because in theory, the distance learning people are listening to this live.
No, everything they're doing is recorded. If they want to listen live, I think there's an option, but nobody is. So the way this works is it's not this computer that is copying everything, it's a device down here.
Gotcha.
So it's like a spy device. It doesn't matter who's logged in, it doesn't matter what's going on, that thing is recording what's going to the screen.
Okay. That makes sense. I'm like the inquisitive child. I just was
It's
wondering.
alright, children are good.
So
I had a couple.
tomorrow will be set with,
I don't think Paul's ready tomorrow. I think he wants to,
I think
you
we
know,
have a lot to digest.
well, I think he would like to get himself reoriented.
I need to...
Probably Paul's first class will be Wednesday. You'll come in between me. Okay. Will you check your key and make sure it opens? Or did you already check it?
Mine no.
No, it's unlocked. If it's green, then it's unlocked. Yeah, it's green right now.
And flash
What happened yesterday was that it was set on the wrong timer, and they swear that they fixed it, but I made them give him access, so he'll always be able to get it. Okay, I'm gonna miss you, but I'm not sentimental type. Actually, I am. So get to work. See you next week. And no, I'm not going to project myself onto the screen. I might do it a little bit, but only to show you just how miserable life can be when you're centered in a closet 3 meters by 2.5 meters. That's my life.
Well, safe travel.
Oh, I'm good. It's a bus ride. I'll show you.
probably we can catch up at, soccer game. But, maybe let's say he's not going to answer either about that thing, So there are so many people in mathematics how they try to figure out the problem. There's really no one, but Dr. Balfour, he figured out already So, so you don't want to, this is very advanced math. So not, you just want this pattern. You have one to think about. One.
The first assignment.
So first assignment, he told me, but it's gonna be I'm not sure it's going to be set as a table pattern, and you have to use these numbers to see the approximation. I'm not sure. Yeah. And there are four assignments. And what the other one is if you ask you to get the data set out from the permeability. In your second part, you have math, petrophysics, fluid flow, and reservoir. In your lecture, if you go online at the website, you have four sections of the lecture: mathematics, which is this part, and then petrophysics, reservoir, fluid flow, and then reservoir flow. So for the second part, you talk about RT law. So you give you some data about porosity and permeability, and try to fit the plot using Excel that we show you last time. Try to find the base empirical model to describe that data set. And the third one, you have to derive the flow equation for gas. So last time when I took it, he wanted us to show the P square didn't work, but I also showed the pseudo pressure work. I think for your class, he would just ask you to show the pseudo, how to derive the flow equation for gas using pseudo pressure, not P square. But in my class, I use P square. I also have to prove the pseudo pressure. And the last one, you mentioned about dimensionless something. I cannot remember. I think four and then research. Project. Yeah. No, 4, 5. And then the other thing was like occupation. It's like 20, 10, something like that. And then that's like the occupation.